There's a place in Tasmania where miners didn't just extract silver, they could actually see it. Not locked inside rock, not hidden in sulfides, not requiring crushing or chemistry, just sitting there as a raw metal, glinting back at them from inside fractures and cavities. In some cases it didn't even look like ore, it looked like something grown. Thin twisting wires of silver, curling through the rocks like metallic roots. That shouldn't exist in Australia, because silver doesn't behave like gold. It doesn't sit there waiting to be found. It hides, it bonds, it disappears into other minerals so completely that even rich deposits can look completely barren to the naked eye. And yet, in a small windswept corner of Tasmania, near Zeehan and Dundas, that rule completely breaks down, and almost nobody talks about it. To understand why this place is so unusual, you have to start with a simple comparison: gold versus silver. Gold is geologically stubborn, it resists change, it doesn't react easily with oxygen, sulfur, or most natural fluids. That's why it survives intact through millions of years of weathering and erosion. It can be broken out of rock, transported by rivers, concentrated into placer deposits, and still remain as visible metallic gold the entire time. That's why panning works. That's why nuggets exist. Gold doesn't need much help to stay in its native form. Silver is the opposite. Silver is chemically reactive. It prefers to bond with other elements, especially sulfur. In most geological systems, silver is locked inside sulfide minerals like argentite or dispersed through galena. Even when a rock contains large amounts of silver, you often can't see it. It's there, but it's invisible, chemically trapped within the structure of other minerals. To actually get silver out of those rocks, you usually need to intervene. Heat is the most common method. Roasting the ore breaks down the sulfides. It drives off sulfur and frees the silver. Without that step, the metal remains locked away. So native silver, actual metallic silver formed naturally, is extremely rare. But here's the part that makes Zeehan and Dundas extraordinary. At this site, nature did the roasting. The geology didn't just concentrate silver, it went one step further and liberated it, breaking it out of its chemical bonds and redepositing it as pure metal. In some cases, that metal formed into delicate wire-like structures, growing into open spaces in the rock as if the earth itself was crystallizing silver in real time. That's not just rare in Australia, that's rare anywhere. The story begins like most hydrothermal systems. Deep underground, hot fluids rich in metals move through a fractured landscape of volcanic rocks and sediments. These fluids carried silver, lead, zinc, and other elements, depositing them into cracks, faults, and brecciated zones as they cooled. At this stage, the deposit would have looked completely ordinary. Silver was present, but locked away in sulfides. If you walked across it, you wouldn't have known what was beneath your feet. But the system didn't stay buried. Over time, tectonic uplift and erosion stripped away the overlying layers of rock, bringing the deposit closer to the surface. And that's when the real transformation began. Oxygen-rich water started to circulate through the fractures. This is where everything changes. Sulfide minerals are stable deep underground, but near the surface, in the presence of oxygen and water, they begin to break down. The sulfur is oxidized, often forming acidic solutions that attack the surrounding rock even further. Metals that were once locked in place are released into circulating fluids. In most environments, that's where things start to fall apart. Metals disperse. They move away from the original deposit. The system loses its concentration. But at Zeehan and Dundas, the conditions were just right. Instead of being carried away, the silver stayed within the system. It moved, but only locally. It dissolved and reprecipitated almost immediately as conditions shifted. Tiny changes in chemistry, temperature, or fluid composition triggering the silver to come out of solution. And when it didn't go back into sulfides. It formed as native metal. This process repeated over and over again. Dissolution, movement, reprecipitation. Each cycle concentrating the silver further and upgrading the deposit in place. What began as a standard sulfide system was gradually overprinted by an oxidized zone rich in secondary minerals, and crucially, native silver. The physical result of this process is what makes the site so distinctive. Instead of dull, massive ore, you get structure, texture, and form. Silver growing into open spaces. Why silver is one of the most striking examples. These are thin, filament-like strands of metallic silver that form in cavities and fractures. They twist, branch, and curl in ways that feel almost organic, like roots or tendrils. They're not carved out of rock, they're built into it, crystallizing directly from solution. Alongside these, you find dendritic silver, branching, tree-like patterns that spread across surfaces. You find spongy masses, irregular blobs, and metallic seams cutting through altered rock. And because it's metallic, it reflects light in a way that immediately stands out. Miners in the late 1800s didn't need assays to tell them they'd found something valuable. They could see it. Their visibility changed everything. When a Zeehan field was discovered, it triggered a rush. The town grew rapidly, driven by the promise of silver that didn't need to be processed in the usual way. Unlike typical deposits where ore had to be crushed, roasted and chemically treated, some of the silver here could be physically separated and smelted directly. It felt different, easier and more immediate. But the real significance of Zeehan isn't just historical, it's geological. Because what happened here is a textbook example of extreme secondary enrichment. The original deposit wasn't necessarily exceptional in terms of grade. What made it extraordinary was the overprinting, the transformation caused by surface processes. And that transformation required a very specific set of conditions. You need a deposit rich enough in silver to begin with, you need permeability, fractures, faults and open pathways for fluids to move. You need sustained exposure to oxygen-rich water to break down sulfides, and you need just the right balance of fluid flow. Not so much that metals are flushed out of the system, but enough to allow redistribution. Miss any one of those factors and you don't get native silver, you just get weathered rock. That's why this kind of system is so rare. It's not just about having silver, it's about having the exact sequence of geological events that can unlock it and rebuild it into a new form. For modern prospectors and geologists, that has real implications. Because systems like this don't just create visible silver, they demonstrate how metals can be upgraded naturally. They show how oxidation can take something invisible and make it visible, and they reveal the pathways for fluid movement and highlight zones where enrichment has occurred. If you're working in a sulfide-rich system, especially one with arsenopyrite or other reactive minerals, these processes are directly relevant. The same chemistry that liberated silver here can, in other contexts, liberate gold. It can create enriched zones near the surface, concentrate metals along structural pathways, and transform the character of a deposit. But it's important to understand a limitation. Zeehan is not the norm. Most systems don't reach this level of transformation. They weather, but they don't upgrade. They break down, but they don't rebuild. The balance required is too precise, too dependent on timing, structure and chemistry, all aligning perfectly. That's why native silver remains so rare, especially in a place like Australia where most deposits formed under conditions that favour sulfide stability. Zeehan and Dundas are the exception. And even here, the story isn't uniform. Not every part of the field produced visible silver. Some zones remain sulfide dominated. Others develop different secondary minerals, like silver chloride, which forms in oxidized environments but doesn't have the same metallic appearance. What you're seeing across the field is a gradient, a transition from primary sulfide mineralization to fully oxidized secondary enrichment zones. And within that gradient, certain pockets reach the perfect conditions to produce native silver. Those pockets are what made the field famous, but they're also what make it scientifically important, because they capture a moment in geological time where a system crossed the threshold, where the chemistry flipped and the behaviour of silver changed completely. Today, the rush is gone, the town is quieter, the easily accessible zones have long since been worked out, but the geology hasn't disappeared. The structures are still there, the altered zones still exist, and the processes that created them are still recorded in the rock. It's just harder to see now, which is fitting in a way, because silver, by its nature, prefers to stay hidden, except here. In this one corner of Tasmania, under the right conditions, it briefly behaved like something else entirely. It stepped out of its chemical cage, reformed as pure metal, and revealed itself in a way that almost never happens. And for a short window in history, that made Zeehan and Dundas one of the strangest, most unique silver deposits not just in Australia, but anywhere on Earth. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.